The final and most common sign number representation that we'll be learning about is called Radix Complement, or also known as 2's complement. Alright, so how do you represent a positive and a negative number in 2's complement? Well, again, positive numbers are just as they are. So if we want the positive number 10, it's going to be the number 10, and it's going to have a sign bit of 0 to say that it's positive. So as you'll see that in every single signed number representation, all the positive numbers look the same. The negative numbers is where it differs. So what if we wanted a negative 10? Alright, so we're going to take the number 10. So take positive 10. Take positive 10. Flip all the bits. Alright, so we're going to flip all the bits. So now we have 1's complement. And now we're going to add 1. So when you add 1, you're going to get these numbers: 0, carry the 1, 1, 1, 0, 1. So this now is negative 10 in 2's complement form. Now you can do this flipping the bit and adding one thing, or there's a special little 2's complement trick. Okay, for the 2's complement trick, what you can do is, instead of flipping all the bits and adding 1, you can just say, okay, here's your 2's complement number. What you're going to do is start from the right, copy down all the numbers until you reach the first one, then toggle everything else. So I'll write that down. Start from the right, copy down all numbers until first one, then flip rest of bits. So here we have now a 2's complement number to tell us that this number here, which we noted was negative, what is that number? Well, that number is a negative. What is this magnitude now? This is 14. So this number 110010 is equal to negative 14 in 2's complement notation. And you found that out by doing the 2's complement trick of flipping the bits and adding 1. Alright, let's practice this a little more. Okay, let's say, what is negative 22 in 2's complement? So we write down positive 22. Positive 22 is going to be 16 plus 4 plus 2. Here's positive 22. And now, to get it into 2's complement, we're going to kind of copy down everything until you reach the first one, and then flip all the bits. So this is your answer. This is your negative 22 in 2's complement. Alright, so what about this number? Oops. Let's say we started off with this number, 110011, 2's complement. So what is this number in decimal? Well, we see that it's a negative number, so in order to figure out what it is, we're going to do the 2's complement trick, which is we copy down everything until we reach the first one. We reached it right away, so we put that 1 down and then flip all the bits. 0, 1, 1, 0, 0. So this number is equal to, what is this? This is a 13. So we know that this is equal to negative 13. So in order to get a feel for all of these, you just kind of have to do them a bunch of times. And remember that in every single sign number representation, all the positive numbers look the same because the magnitude is the same for any positive number and you have a 0 sign bit. What differs is, depending on your representation, is the magnitude to represent negative numbers. And hopefully this lecture has showed you how to do that. Let's look at some sample problems now. This can be found in the textbook. Let's look at some end of chapter problems. Let's try this first one here, number 12. Which of the following two signed binary numbers has a larger magnitude? Assume the numbers are in Radix Complement form. Okay, so Radix Complement form, we've got 1, 1, 1, 0, 1, 1, 1, 0, and 0, 0, 0, 1, 0, 0, 1, 1. Okay, let's write those down over here. Here are two numbers in Radix Complement. Alright, Radix Complement is the same as 2's complement. We note that this is a positive number and this is a negative number. So in this positive number, the magnitude is what? The magnitude is 3 plus 16, which is 19. This is a positive 19. In this number, we know it's negative. How do we find out what the magnitude is? We copy down the bits until we reach the first one and then flip. And what do we have as the magnitude here? 16 plus 2, which is 18. So the answer to this question is the second term has the larger magnitude because the not plus 18, negative 18, because the magnitude here is 19, whereas the magnitude here is 18. Alright, so why is 2's complement, which seems to be the most funny, ridiculous way of representing signed numbers, why is this useful for a computer? Well, this is the only signed signed number representation that has one representation for 0. So with Radix Complement, we can represent the numbers negative 2 to the n minus 1 all the way to 2 to the n minus 1 minus 1. So look at that. We were able to represent one more negative number than we were able to represent positive number. So let's take the case where n equals 4. We can represent the numbers negative 8 to positive 7, whereas before you notice we could represent only negative 7 to positive 7. And why is this the case? Because here we go, here's the number, negative 8. How do we know this is a negative 8? Well, we copy down until we reach the first one, and we reach the first one at the sign bit, so we know this is a negative 8. And we can represent up to a positive 7, which is 0, 1, 1, 1. There is only one representation for 0, and that is 0. If you look at our other case before, we had 1, 1, 1, 1. This is no longer a negative 0. What is this number? Copy down the first one, flip all the bits. 1, 1, 1, 1 is therefore equal to a negative 1.